are used to considering space as an eternal and unchanging ocean of peace where processes last for billions of years. However, today the instruments of the National Aeronautics and Space Administration and data from the James Webb Space Telescope record a disturbing dynamic. Something in the deep vacuum is changing much faster than classical theories predicted, and these metamorphoses are already beginning to directly affect the Earth. From the anomalous behavior of the solar cycle to unpredictable shifts in the flows of cosmic rays, we stand on the threshold of a new scientific reality. Today, we will understand why the future of our civilization now depends on processes in the distant interstellar space. For thousands of years, humanity perceived the night sky as an unchanging decoration, a perfectly tuned mechanism where every star knows its place. Ancient civilizations erected megalithic structures such as Stonehenge or the Pyramids of Giza to track the cycles of celestial bodies, believing in their absolute stability. The sun was for us a predictable source of life, and the night space was a majestic void. However, this illusion of peace began to crumble with the appearance of the first scientific instruments. When Galileo Galilei, at the beginning of the 17th century, directed his telescope at the sun, he saw not an ideally clean sphere, but spots that changed and moved. This was the first evidence that internal processes exist in space that we cannot control and which we are only beginning to understand. Before we begin, write which city you are from so that we know how far our stories travel. And do not forget to subscribe. The true realization that we are not just observing space, but are its integral part came in the 19th century. On the 1st of September 1859, British astronomer Richard Carrington recorded an incredible flash on the surface of the sun. What he saw later received the name Carrington Event. It was the most powerful geomagnetic storm in the entire history of observations. Only 18 hours after the flare, the night sky across the planet lit up with incredible polar auroras. People in the Caribbean islands and in Colombia could read newspapers at night by the light of the sky, which shimmered with red and green colors. But along with beauty came chaos. Telegraph systems across Europe and North America failed. Operators received electric shocks, the paper in the devices caught fire, and messages continued to be transmitted even when the batteries were disconnected, because the wires themselves absorbed energy from the disturbed magnetic field of the Earth. This event became the first serious warning. It proved that our planet is wrapped in an invisible but extremely dynamic shield called the magnetosphere. Understanding the nature of this protection began to form even earlier thanks to the works of William Gilbert, who in the 16th century suggested that the Earth itself is a giant magnet. However, only in the 20th century, with the beginning of the space age, did we realize how fragile this balance is. Scientists discovered that the magnetic field of the Earth is generated deep in its interior, in the molten outer core, where the movement of liquid iron creates a giant dynamo. This shield extends for thousands of kilometers into space, protecting us from the solar wind, a stream of charged particles flying from the sun at a speed of millions of kilometers per hour. In the middle of the 20th century, astrophysicist Eugene Parker theoretically substantiated the existence of the solar wind, which at that time seemed like science fiction. However, missions of the National Aeronautics and Space Administration, such as Mariner 2, confirmed his theory. It turned out that we live in the atmosphere of a star. The sun does not end where we see its fiery disk. Its influence, called the heliosphere, extends far beyond the orbit of Pluto. The heliosphere acts as a giant cocoon that protects the entire solar system from much more dangerous radiation, galactic cosmic rays that come from supernova explosions, and other cataclysms in the depths of the Milky Way. During the last century, scientists recorded a disturbing trend. The magnetic field of the Earth began to weaken. Over the last 200 years, its intensity has decreased by approximately 9%. Moreover, the northern magnetic pole, which previously drifted slowly, is now moving toward Siberia at a speed of more than 50 kilometers per year. Why is this happening right now? Is it related only to internal processes in the core of the planet? Or is the space around us becoming different, forcing the terrestrial systems to react? We began to notice that the 11-year cycles of solar activity are becoming less predictable. In the 80s of the 20th century, a powerful flare caused a complete shutdown of the power grid in the Canadian province of Quebec, leaving millions of people without light and heat. This demonstrated our vulnerability. The more complex our technological civilization becomes, the more we depend on the stability of the cosmic environment. Global positioning system satellites, international financial transactions, internet networks, all this can be destroyed by one powerful coronal mass ejection. But now scientists from the European Space Agency and other leading institutions warn of something larger. Data from the Swarm satellite group show that changes in the magnetic field are accelerating. Simultaneously, we observe unusual behavior of the outer boundaries of the heliosphere. The Voyager 1 and Voyager 2 missions, which have already left the limits of the solar wind, send data about unexpectedly high density of interstellar gas and dust. It seems that the solar system is entering a new region of the galaxy where conditions differ from those in which we have been for the last 10,000 years. This historical excursion leads us to the main question. If we previously considered cosmic threats to be something rare and remote, were we wrong? Perhaps the stability we observed during the development of our civilization was only a short lull before big changes. When we look at the historical data of ice cores and annual rings of trees, we see traces of giant solar storms of the past that were tens of times more powerful than the Carrington event. For example, the Miyake event, which took place more than 1,000 years ago, left behind such a powerful surge of radioactive carbon that it is recorded in the biosphere across the planet. Today we have tools that Carrington or Parker could not even dream of. The Hubble and James Webb Space Telescopes allow us to see processes in other star systems that resemble what is happening with ours. We see stars that suddenly change their activity and planets that lose their atmospheres under the pressure of cosmic radiation. This gives us context for understanding our own fate. We can no longer ignore the fact that the Earth is not a closed system. It is a tiny ship in a stormy ocean of energies, and this ocean is now beginning to change its rhythm. If the 19th century gave us the first hints that the sun is a violent and unpredictable neighbor, then the 20th century allowed humanity to finally break away from the Earth's surface and stretch its electronic fingers to the very borders of our stellar system. This was an era of great hopes when scientists believed that the space beyond the planets was simply an empty and static vacuum. However, every new mission brought data that forced the rewriting of astrophysics textbooks. The most important stage in this process was the Voyager 1 and Voyager 2 missions, launched in 1977. These devices, which were originally intended only for the study of giant planets like Jupiter and Saturn, turned into the most important scouts in the history of our civilization. When Voyager 1 and Voyager 2 completed their main tasks near the distant planets, they continued their journey into the unknown, heading for the border of the heliosphere. For a long time, scientists considered this border to be stable and motionless, like a glass sphere protecting us. However, in December 2004, Voyager 1 crossed the so-called termination shock, a place where the solar wind suddenly slows down, colliding with the pressure of the interstellar medium. This was the first direct evidence that we live inside a dynamic bubble that constantly contracts and expands under the influence of external forces. The device recorded incredible turbulence. Instead of a uniform flow of particles, it entered magnetic jungles where flows of solar plasma mixed with the energies of deep space. Only in August 2012 did Voyager 1 make a historical transition. It became the first object created by man to enter interstellar space. The data it sent to Earth stunned the scientific community. The instruments recorded a sharp drop in the number of solar particles and a simultaneous, almost vertical increase in the intensity of galactic cosmic rays. This meant that the solar shield, despite all its power, has limits. 6 years later, in 2018, Voyager 2 confirmed these observations by crossing the border in another place. Together, these two devices provided us with the first three-dimensional picture of how the solar system interacts with the rest of the Milky Way galaxy. However, the real scientific detective story began when scientists compared the data of the two devices. It turned out that the boundaries of our system are not symmetrical. The solar system looks more like a comet with a long tail flying through interstellar plasma. Moreover, the data showed that the density of the interstellar medium around us is much higher than models from the 40s and 50s of the 20th century predicted. This became the beginning of a new discussion. Have the conditions around our system always been like this? Or are we entering another, more energetically saturated area of space? Parallel to the flights of the Voyagers, in 2008, the National Aeronautics and Space Administration launched a satellite called the Interstellar Boundary Explorer. Its task was to map the boundaries of the heliosphere by recording energetic neutral atoms. What this satellite discovered was a complete surprise for scientists. A bright, clearly defined ribbon appeared on the map of the borders of our system, a narrow strip of extremely intense radiation that literally encircles our system. No existing theory at that time could explain the origin of this structure. It looked like an imprint of the magnetic field of the galaxy on the skin of our solar bubble. This ribbon became the first visual evidence that outer space exerts colossal pressure on us. Over the last 10 years, observations using space telescopes and ground-based observatories have allowed scientists to find out that our sun is now moving through the so-called local interstellar cloud. This is a giant accumulation of gas and dust with an extent of about 30 light-years. For a long time, it was believed that we were in the very center of this cloud where conditions are stable. However, new data indicate that we are at the very edge of this cloud, and soon, by cosmic standards, we may exit it or enter another, even denser zone. This is of critical importance because even a small change in the density of interstellar gas can lead to the compression of the heliosphere. If the solar shield contracts to the orbit of Earth, our planet will find itself face to face with direct hard radiation of the galaxy, which will fundamentally change the state of the ozone layer and the climate. Historical analysis of the last 30 years shows that changes have already begun. We see them not only in deep space, but also in the upper layers of our atmosphere. Data from the satellites of the European Space Agency confirm that the thermosphere of the Earth, a layer of air at an altitude of 100 to 600 kilometers, is beginning to react unusually to cosmic stimuli. Magnetic anomalies that were previously considered isolated cases are now becoming systemic. Scientists such as Professor Daniel Baker from the Laboratory for Atmospheric and Space Physics emphasize that our understanding of the interaction between Earth and space requires a radical update. We can no longer rely on data from the 20th century because the environment around us has changed. This journey into the past helps us realize the stability that humanity considered a given throughout its entire written history may be only temporary geographical luck. We traveled through a calm area of the galaxy, but now this path leads us into more turbulent waters. This is not a conspiracy theory, but a conclusion to which billions of bits of data sent by the Voyagers from a distance of more than 23 billion kilometers from Earth push us. Their weak signals, the power of which is less than 1/billionth of a watt, carry a message that the great space around us has come into motion. And what we see today, from unusually bright polar auroras in tropical latitudes to failures in the operation of navigation systems, is only the first ripples on the surface of the ocean that is beginning to storm. Today we are moving from memories of the past to the disturbing realities of the present. We are in the epicenter of events that force the leading heliophysicists of the world to review their prediction models. The main attention of the scientific community is now focused on the 25th solar cycle. Every 11 years, our sun goes through a cycle of activity change from a calm minimum to a stormy maximum when the magnetic poles of the star actually change places. However, the 25th cycle, which began in 2019, turned out to be completely different from what the experts of the National Aeronautics and Space Administration and the National Oceanic and Atmospheric Administration expected. Initial forecasts by scientists indicated that this cycle would be weak, similar to the previous 24th. However, already by the middle of 2023, the number of sunspots, the main indicator of activity, almost doubled the predicted figures. The sun began to generate flares of class X, the most powerful category, much earlier and more often than mathematical models predicted. Why is this important for us on Earth? Because every such flare is a colossal release of energy, equivalent to billions of hydrogen bombs exploding simultaneously. To study these processes, humanity uses the most sophisticated tools in history. One of them is the Parker Solar Probe, named after Eugene Parker. This device became the fastest object created by man, and it approaches the sun at an incredibly close distance, actually touching the solar corona. Thanks to the data of the Parker probe, we learned about the existence of switchbacks in the magnetic field of the sun, sudden bends of the solar wind that accelerate particles to relativistic speeds. These structures act as giant cosmic whips that hit the surrounding space, increasing turbulence in the entire solar system. Another key tool is the Solar Orbiter spacecraft, launched by the European Space Agency. It takes pictures of the surface of the sun with the highest resolution in history. These shots showed us a phenomenon that scientists called campfires, tiny but incredibly hot flares that constantly occur across the entire surface of the star. It is these campfires, as researchers believe, that are responsible for heating the solar corona to millions of degrees, while the surface of the sun itself has a temperature of only about 6,000 degrees Celsius. Understanding this thermodynamic anomaly is the key to understanding how the sun affects our environment. When solar activity increases, we observe a direct physical impact on the upper layers of our atmosphere. The thermosphere of the Earth, under the influence of extreme ultraviolet radiation, begins to expand. This creates an effect of blowing up the planetary shell. For satellites in low Earth orbit, this means a sharp increase in air resistance. In just one incident in February 2022, the Space Exploration Technologies Corporation lost about 40 Starlink satellites because a small geomagnetic storm caused a sudden thickening of the atmosphere, and the devices simply could not maintain altitude, burning up during the fall. Professor Nicola Fox, Associate Administrator for the Science Mission Directorate of the National Aeronautics and Space Administration, has repeatedly emphasized that we live in an era of extreme space weather. But the problem is not only in the sun. Scientific data from the journal Nature indicate that the magnetic field of the Earth is now in a state of instability. In addition to the general weakening, scientists record the so-called South Atlantic anomaly, a huge area over South America and the Atlantic Ocean, where the protective field is so weak that cosmic rays penetrate deep into the atmosphere, causing failures in the electronics of aircraft and spacecraft. The physics of this process is extremely complex. The magnetic field of the Earth acts as a mirror for charged particles, forcing them to rotate along the force lines in the Van Allen belts. However, when the solar wind becomes too dense or contains the wrong orientation of the magnetic field, magnetic reconnection occurs. At this moment, the energy of space literally pours into our atmosphere. This leads not only to the appearance of bright polar auroras, which residents of middle and southern latitudes now see, but also to the occurrence of powerful induced currents in the Earth crust. These currents can overload transformers at power plants, causing large-scale blackouts. We must also consider data from the James Webb Space Telescope, which, although intended for observing the distant universe, provided invaluable information about the composition of interstellar dust surrounding our system. The latest reports from scientists published in the journal Science indicate that the chemical composition of this dust is changing. This confirms the hypothesis that the solar system is entering a zone with different physical properties. A larger number of neutral hydrogen atoms penetrate through the heliosphere, which in turn changes the balance of ionization in the upper layers of our atmosphere. This is not just a change of weather outside the window. It is a fundamental change in the conditions of our existence as a species. If the sun continues to demonstrate such activity and the magnetic shield of the Earth continues to weaken, we will have to fundamentally change our approach to energy, communication, and even construction. Every breath of our star now echoes in every wire of our world. We are used to considering space as a background for our life, but now we understand that it is an active player whose actions are becoming increasingly unpredictable. Scientists from the Japan Aerospace Exploration Agency, analyzing data from the Hinode mission, warn we may be approaching a superflare, an event that is hundreds of times more powerful than anything we have seen in the last 200 years. Although the probability of such an event remains low, it is no longer zero. Everything indicates that the mechanisms of our sun are working at increased speeds, and the reasons for this may be hidden deep in its interior, where nuclear fusion interacts with powerful convective flows of plasma. If the sun is the engine of our system, then the space through which we travel is the environment that determines the parameters of the operation of this engine. During the last decades, we began to receive data indicating that we are entering a zone of increased density and changed chemical composition. This area is known as the local interstellar cloud, or as astrophysicists sometimes call it, the local fluff. This structure has an extent of about 30 light years, and our sun has been in it for approximately 10,000 years. However, new data from the James Webb Space Telescope indicate that we are approaching the border of this cloud, where the physics of the interstellar medium changes sharply. To understand the scale of the problem, it is necessary to imagine a dynamic equilibrium. On one side, the pressure of the solar wind acts, blowing up our heliosphere like a giant protective bubble. On the other side, interstellar gas, dust, and the magnetic field of the galaxy press in. For a long time, these forces were in balance, but now we see signs that the external pressure is growing. When Voyager 1 and Voyager 2 crossed the heliopause, they recorded an unexpectedly high plasma temperature outside our system, about 40,000 degrees Kelvin. This is significantly higher than models from the 80s of the 20th century predicted. This means that the interstellar medium around us is much more energetic than we previously thought. The James Webb Space Telescope, using its ultra-sensitive instruments in the infrared range, provided us with a detailed picture of the composition of this environment. Scientists have discovered an increased concentration of large particles of interstellar dust. This dust does not just fly in space, it interacts with the magnetic field of the sun. When the solar system enters a denser part of the cloud, neutral hydrogen atoms begin to penetrate deep into the system, ignoring the magnetic shield. These atoms collide with particles of the solar wind, slowing it down and forcing the heliosphere to contract. If this compression continues, the boundary of the heliosphere may approach the orbits of the inner planets. This will mean that Earth will start receiving dozens of times more galactic radiation. Dr. Jeffrey Linsky from the University of Colorado, one of the leading experts on the interstellar medium, notes that we observe heterogeneity in the distribution of matter in the local cloud group. This means that the conditions of our system journey can change literally within one human life. This is confirmed by findings of iron-60 isotopes in sediments at the bottom of oceans and in the glaciers of Antarctica. The iron-60 isotope is not produced naturally on Earth. It is born only during supernova explosions. The presence of this isotope in layers that are only a few thousand years old proves that we constantly collect cosmic sediment during movement through the galaxy, and now this flow is becoming more intense. Moreover, we must take into account the role of the magnetic field of the Milky Way galaxy itself. Data from the Interstellar Boundary Explorer mission demonstrated that the direction of the galactic magnetic field lines exerts a powerful influence on the shape of our heliosphere, making it asymmetric. We are not just flying forward, we are literally tearing through magnetic resistance. Modern research published in Astrophysical Journal Letters suggests that we are now crossing the boundary between the local interstellar cloud and the so-called G cloud, another gas accumulation with different characteristics. This transition is accompanied by increased turbulence, which is recorded by our instruments as inexplicable anomalies. What does this mean for a human? Increasing the flow of neutral hydrogen and galactic cosmic rays affects the chemistry of our atmosphere. When these high-energy particles crash into nitrogen and oxygen molecules, they create cascades of secondary particles that can reach the surface of the Earth. This affects the formation of clouds and, therefore, the global climate. There is the Svensmark hypothesis, which links the intensity of cosmic rays with the cloudiness of the planet. If the heliosphere weakens under the pressure of the interstellar medium, we may see radical changes in the regime of precipitation and temperatures around the world. Scientists from the European Space Agency, working with data from the Gaia telescope, Also draw attention to the fact that the trajectory of the sun in the galaxy is not ideally straight. We make oscillatory movements relative to the galactic plane. Every time we approach areas with a higher density of stars or gas, the risk for the biosphere increase. We are now in exactly such a period when external factors begin to dominate the internal cycles of the solar system. Thus, the scientific base tells us the following. Earth is not an isolated island, but part of a large galactic system of matter and energy circulation. The changes that we record with the help of the James Webb Space Telescope and the Voyagers are not an error of instruments, but evidence that we are entering a new climatic and energy era of space. We are only beginning to understand how these giant mechanisms affect our daily lives, from the stability of power grids to the health of living organisms. The following decades will become critical for learning how to predict these galactic tides and adapt to them. When we encounter phenomena that do not fit into standard models, science finds itself at a crossroads. Today we enter the field of hypotheses that only yesterday seemed marginal, but today become the subject of serious discussions within the walls of the European Organization for Nuclear Research and leading universities of the world. The main question that divides the scientific community sounds like this. Are the current changes in the solar system the result of the internal evolution of our star, or have we witnessed the influence of a much larger galactic mechanism? One of the most discussed and at the same time controversial theories is the hypothesis about the influence of galactic cosmic rays on the cloud cover of Earth. Its author is the Danish physicist Henrik Svensmark. The essence of the theory is that the flow of high-energy particles from deep space crashing into the atmosphere of our planet ionizes air molecules, creating seeds for the formation of clouds. When the magnetic field of the sun and the heliosphere are strong, they deflect these rays, there are fewer clouds, and the planet heats up. However, now, when the heliosphere demonstrates signs of instability, the flow of cosmic rays is increasing. To verify this bold idea, an experiment called CLOUD was created at the European Organization for Nuclear Research. Scientists use a particle accelerator to simulate cosmic radiation in a special chamber that reproduces the conditions of the Earth atmosphere. Preliminary results confirm cosmic rays can indeed contribute to the formation of aerosols. If this theory receives full confirmation, it will mean that the climate of Earth literally breathes in time with the processes taking place in our arm of the Milky Way galaxy. However, the discussion goes even deeper. Some researchers point to a strange synchronicity of anomalies on other planets of our system. Over the last 20 years, we have recorded incredible changes. Giant cloud bands disappear and appear on Jupiter. Saturn demonstrates a change in the activity of its ultra-powerful storms. And Neptune suddenly began to demonstrate anomalous cooling that cannot be explained only by the solar cycle. Could this be a sign that the entire solar system is entering a zone with a higher energy potential? An alternative point of view actively developed by specialists from the Space Research Institute is that we are observing the effect of a galactic crossing. Our solar system makes vertical oscillations relative to the plane of the galactic disk. Every 30 million years, we pass through the most dense zones of the galaxy. Although now we are formally located slightly above the plane of the disk, we are entering the so-called local bubble, an area of space cleared by supernova explosions millions of years ago. The boundaries of this bubble are not smooth. Scientists suggest that we are now crossing one of such fronts of interstellar matter, which causes the effect of heliosphere compression. Special attention of scientists is attracted by the so-called heliospheric current sheet, the largest structure in the solar system, resembling a ballerina skirt that rotates together with the sun. It separates areas with different polarity of the magnetic field. Recent observations show that this sheet has become more wavy and turbulent. This causes an increase in electric currents in the plasma that fills the interplanetary space. These currents, interacting with the ionosphere of Earth, can cause the same unpredictable weather anomalies and seismic activity that we have been observing in recent years. It is worth mentioning the research of Professor Pekka Pulkkinen from Finland, who studies the connection between cosmic currents and plate tectonics. Although classical geology is skeptical about external influence on the Earth interior, Mathematical correlations between peaks of solar activity and the number of powerful earthquakes are becoming increasingly obvious. The hypothesis is that powerful geomagnetic induced currents can create microheating in fault zones, acting as the last drop for the accumulated stress in the lithosphere. The scientific world is now divided into conservatives who try to explain everything by internal cycles and universalists who call for considering Earth as part of a large electromagnetic chain of the galaxy. Recent reports from the National Aeronautics and Space Administration regarding the state of the magnetosphere of Uranus and Neptune only add fuel to this fire. If the giant planets located billions of kilometers from the Sun demonstrate radical changes in the atmosphere simultaneously with Earth, then the cause must be external. This is not just a dispute about numbers and tables. This is a fundamental paradigm shift. If we are only part of a galactic mechanism, then our future depends on events that took place thousands of light years away from us. From supernova flares whose radiation has finally reached our borders, or from the movement of dark matter that can change the gravitational balance of the system. In this part of our analysis, we must admit, science does not yet have a final answer. We are in a state of a great data gathering. Every new shot from the James Webb Space Telescope, every signal from the dying Voyager is a piece of a giant puzzle. We see that the rules of the game are changing, but we do not yet see the player himself. However, it is these alternative theories today that prepare the ground for discoveries that in 10 or 20 years will become the basis of the new physics of the universe. When we consider global changes in space, it is impossible to ignore what is happening directly under our feet in the very heart of our planet. One of the most discussed alternative theories in modern geophysics suggests that the changes we observe in the distant space have a direct resonance with processes in the Earth core. Scientists from the European Space Agency, analyzing data from the Swarm satellite constellation, record not just a weakening of the magnetic field, but its destabilization, which may be a response to external energy stimuli. Special attention of the scientific world is now focused on the phenomenon that received the name South Atlantic Anomaly. This is a giant area over South America and the southern part of the Atlantic Ocean where the intensity of the magnetic field of Earth is much lower than in any other place on the planet. During the last decades, this anomaly has not only grown, but also began to divide into two separate centers of minimum intensity. Some researchers put forward a bold hypothesis. This is not just a random fluctuation, but a harbinger of a complete inversion of the magnetic poles of the planet. The last such event, known as the Lachamp excursion, took place approximately 41,000 years ago. Then the magnetic shield of Earth almost disappeared for several centuries, which led to a sharp increase in the level of cosmic radiation on the surface, and, as some paleontologists suggest, contributed to the disappearance of large mammals and changes in the development of human populations. An alternative point of view considered in the National Aeronautics and Space Administration is that we are observing a so-called magnetic excursion, a temporary disturbance that will not lead to a complete reversal, but will make our atmosphere much more vulnerable to solar flares of Class 10. This creates an urgent need for new observation tools. One of the most important missions of the future is the launch of a spacecraft called the Interstellar Mapping and Acceleration Probe. This mission, developed at the Applied Physics Laboratory of Johns Hopkins University, aims to place a high-tech station at Lagrange point number 1, at a distance of about 1.5 million kilometers from Earth. The main task of the Interstellar Mapping and Acceleration Probe is to investigate in detail that same mysterious ribbon of energetic neutral atoms at the border of the solar system, which the Interstellar Boundary Explorer device first discovered. Scientists want to understand exactly how galactic cosmic rays penetrate through our heliospheric shield and why their intensity has begun to change in recent years. Another ambitious project is the Solar Cruiser mission, which is based on the technology of a solar sail of a huge area. This device will be able to stay in a position between the Sun and Earth for a long time, working as an early warning system. It will allow recording parameters of the solar wind several hours before they reach our magnetosphere. This will give us critically important time to switch power systems and satellite networks to a safe mode. In addition, the European Space Agency is considering the possibility of creating a network of small satellites called Vigil, which will be located at Lagrange point number 5. This will allow us to literally look over the horizon of the sun, observing active regions even before they turn toward Earth as a result of the rotation of the star. Scientific debates also revolve around the question, can we artificially protect our planet from increased cosmic radiation? In the theoretical works of astrophysicists published in the journal Planetary and Space Science, the concept of creating a giant magnetic dipole at Lagrange point number 1 is proposed. Such a device would be able to create an artificial magnetosphere that would deflect charged particles even on the approach to Earth. Although today it sounds like science fiction, the speed at which changes occur in the surrounding space may force humanity to implement these projects much faster than we planned. We must also mention the future Interstellar Probe mission, on which hundreds of scientists around the world are currently working. This will be the first device designed specifically to go beyond the limits of the heliosphere to a distance of up to 1,000 astronomical units from the Sun. Only by being in the pure interstellar space will we be able to see our solar system from the side and finally understand whether the changes we record are the result of moving through a dust cloud or whether it is part of a global process in our sector of the galaxy. All these missions and theories are united by one thing: the realization that we can no longer be passive observers. If the space around us becomes different, our civilization must evolve technologically to preserve its home. Scientists warn that the window of opportunity for creating a global system of cosmic security may be limited. That is why the next decade will be decisive in our understanding of how to survive in the conditions of a new cosmic reality. We continue our review of the technological arsenal that humanity is preparing for an encounter with the unknown. If the previous decades were the era of lone pioneers, then the 2020s and 2030s will become the time of creating a global and even systemic network of cosmic monitoring. One of the cornerstones of this new strategy is the Nancy Grace Roman Space Telescope, the launch of which is planned by the National Aeronautics and Space Administration for 2027. This instrument is not inferior in power to the Hubble telescope. However, its main advantage lies in an extremely wide field of view. It is 100 times larger than that of Hubble, which will allow us to create panoramic shots of space with incredible detail. For our research, this is critically important because the Nancy Grace Roman Space Telescope will be able to record the smallest changes in the distribution of interstellar dust and gas penetrating our solar system. We will finally be able to see the dynamics of galactic tides in real time. Parallel to the American colleagues, the Japan Aerospace Exploration Agency is preparing the Lightbird mission. This spacecraft is designed for the study of cosmic microwave background radiation, the echo of the Big Bang. However, scientists expect much more from this mission. Lightbird will be able to measure the polarization of light passing through the magnetic fields of our galaxy. This will allow us for the first time in history to build a three-dimensional map of the magnetic structure of the Milky Way in our region. If the theories that the changes in the solar system are caused by interaction with powerful galactic magnetic lines are correct, it is the Japanese probe that will provide us with undeniable evidence. However, modern science is not only about giant telescopes, but also about large arrays of data. Today we enter the era where artificial intelligence becomes the main astrophysicist. The volume of information coming from modern observatories is measured in petabytes. The human mind is simply not capable of processing such a quantity of signals simultaneously. That is why the National Aeronautics and Space Administration and the European Space Agency are actively implementing machine learning algorithms for the analysis of solar activity. Artificial intelligence is already today capable of identifying patterns in the magnetic fields of sunspots several days before they turn into powerful flares of Class X. This gives us hope for creating a reliable system for predicting space weather, which will allow protecting our digital networks from a solar strike. Another revolutionary concept currently being developed in scientific centers is the deployment of a network of CubeSats or small satellites throughout the solar system. Imagine thousands of tiny devices forming a giant sensor array. Such a system will allow us to measure the density of the solar wind and the intensity of cosmic rays simultaneously in many points of space. This will allow scientists to see how cosmic storms spread from the sun to the very borders of the heliosphere. This is no longer just observation. It is a transition to full control over the information field of our stellar system. One cannot ignore the Interstellar Probe Project, which is currently at the stage of detailed planning. This is a mission designed for 50 years. The device must develop a speed of more than 70,000 kilometers per hour to go far beyond the limits of the solar bubble. Only by being in a real interstellar environment at a distance of about 900 astronomical units from the Sun will we be able to see our system as a single whole. Scientists plan to equip this probe with instruments for studying the direct influence of galactic plasma. This will allow us to obtain reference data with which we can compare changes on Earth. An important aspect of future research is also the study of the influence of cosmic changes on biological systems. Within the Artemis program, which provides for the return of man to the moon, a series of experiments in deep space are planned. On the Lunar Orbital Station Gateway, modules will be installed for studying how long-term stay under the influence of galactic cosmic rays affects the structure of the deoxyribonucleic acid of living organisms. This knowledge will become the foundation for the future colonization of Mars and other planets, because we must know how to protect a human in conditions where the natural shields of the planet begin to weaken. Thus, future missions and the newest instruments are not just a whim of scientists, but a vital necessity for our technological civilization. We are creating a global system of monitoring and protection that will allow us not just to observe changes in space, but also to adapt to them. We are learning to live in unison with the great pulse of the galaxy, using the most advanced achievements of our mind. Now we are approaching the moment of truth, where all the fragmented pieces of our cosmic detective story fold into a single, although disturbing, picture. We have considered the anomalous behavior of the 25th solar cycle, recorded the weakening of the magnetic shield of our planet, and heard weak signals from the Voyagers reporting the growing pressure of the interstellar medium. The synthesis of these data leads us to a fundamental conclusion that fundamentally changes our place in the universe. Earth can no longer be considered as a closed, autonomous system. We are part of a large galactic organism, and what we are now observing is the beginning of a large-scale energy restructuring of our entire stellar system. During the last 10,000 years, the period we call the Holocene, humanity enjoyed incredible cosmic stability. This was a time of the great lull when the sun was predictable and the space around us was relatively empty. It was this stability that allowed us to build cities, develop science, and create a global digital civilization. However, today, science tells us that this period of grace is coming to an end. We are entering an era that astrophysicists are beginning to call the dynamic cosmos. This is a state where external factors, from the density of interstellar gas to the intensity of galactic rays, begin to directly dictate the conditions of life on our planet. The physics of this process is extremely deep. When we say that something in space is changing, we mean a change in the balance of forces at the boundary of the heliosphere. Our solar bubble, which has protected us for millions of years, is beginning to contract. This is not just a theoretical model. It is a physical reality confirmed by an increase in the flow of secondary particles in our atmosphere. Scientists from the Space Research Institute point out that even a slight increase in the amount of neutral hydrogen penetrating through the solar wind changes the electromagnetic profile of the entire solar system. This affects everything, from the lifespan of satellites in orbit to the chemical reactions in the ozone layer that protect us from deadly ultraviolet light. This leads us to a philosophical break. For a long time, we considered ourselves masters of Earth and space only as beautiful decorations over the head. Now we realize that we are passengers on a tiny ship entering a zone of turbulence. This realization forces us to rethink the very concept of security. Global problems such as climate change must now be considered not only through the prism of industrial emissions, but also through the prism of cosmic energy. If galactic radiation indeed affects the formation of clouds, as proponents of the Svensmark theory claim, then we are faced with a challenge that goes far beyond our planet. The scientific community is now in a state of a great review. Leading journals such as Nature and Science publish research that only 10 years ago would have seemed too bold. We see how astrophysics becomes part of our daily life. When we talk about changes in space, we talk about why navigation in your smartphones becomes less accurate, why polar auroras descend to latitudes where they were never seen, and why scientists with such persistence call for creating protection systems for power grids. This is not conspiracy theory. It is the adaptation of a species to new environmental conditions that have become much larger than we used to think. The culmination of our understanding lies in the fact that these changes are not necessarily catastrophic, but they are inevitable. This is a challenge to our ability to predict and act as a single biological species. We stand on the threshold of discovering new laws of physics that describe the interaction of the biosphere with the galactic environment. This is the moment when humanity must grow up and understand. We live in an ocean of energies, and now this ocean is beginning its new tide. Our ability to decipher these signals and prepare for them in time will determine what the next millennium will be like for terrestrial civilization. These changes that we observe in the depths of space raise questions for us that go far beyond physics or astronomy. If the universe around us passes into a new phase, what does this mean for a human as a biological species? Scientists who study cosmic biology note that we are the product of extremely specific conditions that prevailed in the solar system during the last few million years. However, evolution was never a static process. It was always a response to external pressure. Today, this pressure comes not from jungles or oceans, but from the vacuum itself. We must realize that the strengthening of cosmic radiation and the destabilization of the magnetic shield of Earth are factors that directly affect our deoxyribonucleic acid. High-energy particles capable of piercing the atmosphere can cause microscopic damage in the genetic code of living organisms. However, nature has an amazing ability to adapt. Some researchers suggest that periods of increased cosmic activity in the past became catalysts for genetic jumps, accelerating mutations and the appearance of new traits. Perhaps we stand on the threshold of a biological renewal where humanity will be forced to develop new mechanisms of protection at the cellular level. From a technological point of view, these changes force us to review the very concept of our infrastructure. We can no longer afford to build power grids vulnerable to solar storms or satellites that fail from one powerful flare. We need a planetary shield, not only magnetic, but also technological. This means moving to autonomous, distributed energy systems and creating new materials capable of withstanding extreme particle flows. A philosophical look at the current situation opens to us a majestic and at the same time humble truth. We are used to considering ourselves separated from the universe, observers looking at it through the glass of illusion. But now this glass is broken. We feel the breath of the galaxy on our skin. This forces us to abandon anthropocentrism, the belief that we are the center of everything. Instead, we must accept the concept of galactic ecology. Earth is not just a home, it is a complex cell in the large body of the Milky Way. And if the environment around the cell changes, it must all be rebuilt to preserve life. Scientists from leading universities of the world are increasingly saying that the future of humanity depends on our ability to become cosmically literate. This means understanding that every step of ours on Earth must be coordinated with space weather and the cycles of our star. We are learning to be not just residents of the planet, but citizens of the solar system. These changes in space are not the end of our world. It is the end of our childhood as a civilization. We are forced to go beyond our cozy cradle and learn to live in a real, stormy, and incredibly interesting universe. Summarizing the scientific synthesis, we see that every aspect of our life, from health to the global economy, is now firmly connected with what is happening outside the atmosphere. This requires from us a new solidarity. Cosmic threats do not recognize state borders. A solar flare or a change in interstellar pressure affects everyone equally. Thus, space becomes that very factor that can finally unite humanity around a common goal: survival and prosperity in conditions of a great transformation. We are completing our 2-hour journey through space and time, but the true story of our interaction with space is only beginning. Everything we talked about today, from anomalous solar cycles to the compression of the heliosphere under the pressure of interstellar clouds, testifies to one great truth: we can no longer afford the luxury of ignorance. Space has ceased to be just a distant picture. It has become a factor of our security, our health, and our common future. Scientists warn us not to sow fear, but to awaken our curiosity and responsibility. Every change in the magnetic field of Earth, every new flare on the sun, and every signal from distant probes are calls to action. We must invest in science, support space missions, and develop technologies that will make our civilization resistant to any galactic storms. The stability of the past was a gift, but the future is something we have to build ourselves armed with knowledge. Humanity has always been a species of explorers. We survived ice ages, conquered oceans, and built great empires. Now our next frontier is to learn to live in unison with the rhythms of the Milky Way. We are the eyes and ears of the universe through which it knows itself. And if today something in space is changing, it only means that the time has come for us to become different, wiser, more united, and more conscious of our cosmic role. Thank you for spending these 120 minutes together with us, diving into the most complex and important questions of modern science. Your attention and your support of fundamental knowledge are what allow us to continue this work. Do not forget to subscribe to the channel, put likes, and share this video with those who strive to know the truth about our world. Write in the comments what you think about these cosmic changes. We will definitely read every review of yours. Remember, the sky over our heads is not a border, it is only the beginning of our great journey. Until we meet in new episodes where we will continue to follow the pulse of our incredible universe, take care of yourselves and stay with science.